Yeah.
All right. My name is Jay. This is the FilAm Foundation and my proposal for Nexus Tower. I am the all-around engineer since I did all of it. I know you guys can read it. You guys have been through this many times. You already know what's about to happen. So we'll just get right to it. So introduction, this is going to be on 285 Fulton Street, New York. This is going to be where the World Trade Center, just because it's like basically the heart of New York City. That's how I feel. So the building footprint will be a total of 36,250, and then the max length for the width and the length would be 200 feet. And then the height is a 40-story, so like, and typical floor height is 15, so would be a total elevation of 600 feet. So design standards, we have the deflection limits that is going to use for dead and live load of L/2 fire resistance, and has durability and is much cheaper, and also can handle a lot of environment weathers. So for the weights would be, for steel would be the self weight 490 pounds per cubic feet, and then for concrete 150 pounds per cubic feet. So this is the floor framing layout. So we have the typical right over here. Shear studs would be 12, camber would be 0.75, and then the beam span is around 25. All the beams usually are 25 except for these. And then for girders, they're usually ranges from 35, 15. And these are some of the beams that was used. So for fireproofing, we have a total slab depth of 7.5. That includes the concrete and the metal deck. Concrete being 4.5, and then 4.5 inches, and then metal deck 3 inches. And so that will meet our requirement for the 2-hour fire rating. And then the load combinations were used were for phase 1, we got general system, the good stuff. So for the concrete shear walls and coupling beams, this helped kind of reduce some of those lateral forces. And then for the I use an outrigger system. So basically there's a bracing around 20 to 22 by 14 by 342. And then, so basically my initial design, under the service wind load, we're using under service wind load, we have an allowable displacement of 14.4. And then for the first design, I used 24 inches, 4,000 PSI for the whole floors, for all shear walls. And then design 2, I did for floors 1 to 20, 30 inches, 9,000 PSI. Floors 21 to 31, 28 inches to 9,000 PSI. And then floors 31 to 40 is 24 inches, 8,000 PSI. And it gave me the 17.5 inches displacement in Y direction, which still doesn't make our allowable displacement. So what I did is I added an outrigger truss of that 14 by 342. So you can see finally we're here. I mean, over X direction, you can see the allowable 14.4 and everything is within that. But for the Y direction, we see design 1 way past it, design 2 almost getting close to it, and design 3 finally making it 10.32 displacement. So the total effective design would be 10.3 inches displacement. So everything was reduced from the first initial design was 22.7 inches. So now we have the shear force under ultimate wind load and the bending moment under ultimate wind load. X direction on the top, Y direction, same thing. You can just see like where the outrigger truss is showing where these pipes are coming from, but basically it's just redistributing the load. We have this column analysis. So the left shows the visual that the bracing is holding up, basically underestimating everything that's down here. So this kind of shows that we might have to require some column design, increasing some sizes. But if we do a construction sequence analysis, which is a method to just simulate what happens in the real construction phase, where it would we would just be adding the outrigger truss at the end, showing now it kind of shows ideally the distributed load, force load that's acting on the axle. So foundation design, so I used the soil bearing capacity of 20 kips per square feet and then module subgrade for 480 kips per cubic feet. I may have over-designed the thickness to 144 because I tried to make sure maybe I don't have to do a rebar. But the concrete strength was 6,000 PSI, and these were the load cases that were used. And then so soil pressure deflection diagram for a dead load and a live load, you can see that it should stay on the compression right there by the core. And then with the wind Y direction, you can see that going up. And then for the wind X, you can see how the stress is going more towards the right direction. So our shear stress we have for ACI, that's like 232.3. I know around these, for these loads, combination loads, I believe it went up around 250. So you can see some of this, but these are just around the core. And you can see how like around wind, you can see that how it's moving with the wind load. So I think I might have to readjust that. But for the finite element, so everything on top and bottom bar size is number 11 with a bar spacing at 6 inches. It shows that just at the core we might need some additional rebar. So is for direction 2 as well. And then for a strip base, kind of shows that these are just same thing, top and bottom bar size, number 11. Has a better visualization of where we might need those additional rebars, I mean. And then conclusion, this is the material takeoff. Only thing you need to know are the total for the steel ton and the cubic yards for concrete. So this structural material cost might range around 12.5 to 20 million. I don't know, I could be wrong with that, but overall cost, it's going to be 15 to 20% of the project's overall cost, because that doesn't include like labor costs or like specific materials that are being used. So challenges, learning ETABS was difficult for me. ETABS was giving me a hard time all the time, always crashing on me. But I also learned a lot by just using ETABS as well, because I haven't really worked with 3D. I'm a CAD person, because that's what I'm going to be doing in my job soon. So this is kind of cool to just see like a 3D. I'm actually working on 3Ds now. And then understanding diagrams to address and to rectify any structural failure. Like at first I didn't really understand everything that was going on, but thanks to Professor's videos, that was actually very helpful. And cross-checking ETABS by hand, just to make sure that everything, that's what I learned too, like just making sure everything is good. I'm always trying to do the double checking, and I think that's a good habit. Foundation design and just assessing soil. I've never really worked with soil before besides theory, so this is probably the closest thing. But actually just being able to do everything on my own and just like putting this all together, I have this like better understanding of how like those structural work overall. And then these are references, and that's it.